first-year master's student here. So I'm going to talk about the measurement of high-speed railway subsidence. So the motivation of this project is because in Taiwan we have a high-speed rail built in 2007, and then the Taiwan government water resource department found that there's a land subsidence that is in the southern part of our island that is sinking like 6.6 centimeters every year. So there's public concern about whether the train safety will be affected, since the high-speed railway will be operating in around 300 kilometers per hour, which is 83 meters per second. So it's very dangerous if you have the subsidence that will affect the train safety, and the train will get derailed if the vertical displacement of the train is over 1 centimeter. So 1 centimeter will cause a red light, and then you cannot operate the high-speed rail under that condition. So this is the map of the Taiwan high-speed railway map. And yeah, as I said before, there's major public concern around the southern part, particularly in the Yunlin station, which is in the middle around there's a wide Yunlin station. And then, yeah, I say there's 1 centimeter is considered very dangerous to the high-speed railway operation. And then the Taiwan high-speed railway company, they use the traditional geodetic monitoring to manually monitor the vertical subsidence along their tracks where the train is not operated, like in the midnight. So they'll go climb up to the tracks, and then they'll do the vertical optical leveling on the tracks and in the midnight for 4 or 5 hours. And they will do that occasionally, like 1 month, one time. And this is very time consuming and labor intensive and expensive. And also at that time, because this problem caused the public to panic, and even the high-speed railway company come out and assure people that there is no safety issue, people wouldn't understand and wouldn't believe. So it's important for us to find a way to measure that subsidence value rather than this method. So I come up with a device that we have a accelerometer with a laptop. So this idea is actually come with a quick catcher network life. So I get inspired by the quick catcher network. So they use laptop as a small seismometer that plays in every household to measure earthquakes in the California area. So I want to utilize this device to help me to measure the vertical length subsidence of the high-speed rail. So first, I will test the reliability of the device, and then the data is recorded by the laptop and with the quick catcher network live. So there's a 2-axis accelerometer sit inside the laptop. And then I will do the calibration of the accelerometer before I went to measuring the data. Also, I will correct for the gravitational acceleration for our longitude and latitude in the location of the Earth. And first, I will go for trial rides of the full train route from the first station of the Taiwan high-speed railway to the last station, which is from north to south, and then I'll go from south to north. So I will record the Z component of acceleration of the route from Taipei station to Zuoying station, which is from the north to the south. And then I will also record the south to the north. So because there are 4 tracks for the Taiwan high-speed railway, you have to measure individually for each track. So each track may have different values of the subsidence, which distributed in that track. So I will label the track for my convenience to record which track I'm recording and which direction I'm going. So for south to north, we'll have 1, 2, 3, 4 tracks. For first track and the second track is northbound, and then the third track and fourth track is southbound. So the train always go on those tracks for south and for north. Yeah. So this is the device inside the train. So I will have a GPS, handheld GPS. So the adapter will place on the floor of the first train when the direction is going. So for the southbound, I will place it on the 12th train, and then for the northbound, I'll place it on the first train. So you don't have the effect of the train connection that causes more chaotic vibrations. So I place the accelerometer with the laptop, and on the trolley placed vertically on the first bogie, which is in the very front of the train, and then behind the cabin, the driver's cabin. And then I'll have a handheld Garmin GPS to help me locate where I am to find where the location have the subsidence value. And I also record the screen to simultaneous for synchronization when I go back and then look at the data, and I can like synchronize where I am and where the data is. So this is the normal condition versus the subsidence area. So on the left, you have the very calm like record. So the green is the Z component, and the orange is the Y component, which the train is going. So if you have the train accelerating, then you have the data recorded in the y-axis that is like positive when the train is accelerating, and then negative when the train is deaccelerating. And for the green one, that's the vertical component. So you can see at the right is in some area that have like strong motion in the car, and then you can record that by the accelerometer. So this is the primary preliminary dictation of the southern part, which you can see there's small. There's some subsidence area that causes the vertical displacement, but it's not very big. And then we also found that actually it's not as the media claim that the southern part is more like dangerous to the train. It's actually there's a north part that have larger subsidence value. So actually although the southern part of the country has the large subsidence, but it actually doesn't affect the train. And there are some places that we didn't notice have larger acceleration value for the high-speed railway. So this is the location of the northern part. We go there and then take pictures and then locate it where the large subsidence occurred. And then, so this is the ensemble average of the subsidence signal for that particular area for track 1 and track 2. So this data plots 30 time ensemble average, and then the arrow bar is the one standard deviation of 30 record and 29 record for track 2. And then you have track 3 and track 4 on the same location, same GPS location, but different tracks. So we go like on several rides and then to take a repeated measurement to get a more like consistent result of the subsidence signal. And then we'll calculate the subsidence value from the spectrum of the acceleration data, and then we'll divide it by the frequency twice its corresponding frequency. So we get the displacement, and then we can get a rough estimation of the subsidence value at that location within that time frame. So track 1 and track 2 is around 0.65 centimeters, and the error is calculated with the non-disclosure manual measurement data from the Taiwan High-Speed Railway, which is 1.56%, 1.45% for track 1 and track 2. And then for track 3 and track 4, the subsidence value is like underestimated a little bit. And then the reason that is because when the suspension system is still functioning properly, the damping effect of the whole train coupling with the bogie, with the air spring, the whole nonlinear system, and with the ground with the track, you have to be considered. So you can adjust that and then find out that you can correct the damping effect and then have higher subsidence value that match the manual measurements. So we also went with trial ride and discussion after we have our results published, not published in the journal, but some media found out and then just reported. And then so they invite us to go with them and then have trial rides on other on-site measurements. And then we will compare our method to prove that our method actually working. So we go on other places that they have measurements, but we don't know the measurement value. And then we compare, we just have one ride and then calculate the result after that ride, and then say that is the result comparable to their measurements. Yeah. So the conclusion is after scanning the whole route, the most subsidence area for the Taiwan High-Speed Railway is actually in the northern part, not the southern part. And then because the southern subsidence is distributed more uniformly, so it actually does not create a sharp transition of displacement for high-speed railway, which will not affect the safety of the high-speed railway operation. So we can apply like a seismometer inside the train to measure the subsidence value from the train, and we can like reduce the cost of the measurement, and it's more or less labor intensive. And I also got a patent, but it's all expired. So yeah, so that's it.